Hello everyone. In the first part of this lecture, we went through how to estimate beta 1 and beta 2, and how to report your results, how to interpret the results, and how to do this using eViews as well. So we learn how to calculate or how to estimate beta 1 and beta hat using those formula, and I show you how to do this using eViews as well. In this video, as I explained in the previous videos, I'm going to look at hypothesis testing, but before looking at hypothesis testing, which is probably something that I'm going to cover in the next lecture this week, but in this video I want to focus on interval estimation, which is very important to understand hypothesis testing. So let's first start why we do hypothesis testing. The first stage in statistical inference we already did by learning how to do the estimation. The second stage is how to test hypothesis, and to understand this we really need to understand the difference between point estimation and interval estimation. So what we actually do, or what we actually have from the OLS estimators, we have point estimation where we have single values for beta 1 and beta 2. Remember in our example in the first part of this lecture, we had the final mark, which is y hat here in this equation, and this depends on the estimation for beta 1 here is 11.185, and so that's a single value for beta 1 plus a single value for beta 2, which is 0.726 xi. So here final marks depends on attendance, and we already estimated beta 1 and beta 2. So what we have here, we have single estimate, and we understand if you change the sample, these values will be different. And well, we understand in repeated sampling before, as I explained in the lecture last week, and also the first part of this lecture, we explained that in repeated sampling we expect that the mean value should be equal to the true value. But the question comes now, how reliable is this estimate? So to do this in statistics, so the sampling variability, or the changing the value from according to what sample, or from sample to sample, this for the OLS, so this is given by the variances and the standard error. So the idea here, if we can, let's say this 0.7, the estimation for beta 1. So if you could somehow have or construct an interval where there's a value above and below this 0.7, and within this interval we're somehow confident that the true value will lie between these two intervals, or between these two values, and it means within this interval. So if we're confident, let's say, or 90% chance that, or 95% say chance that this value of the true parameter will lie between these two values or within that interval, that if we can do that, or if we can obtain such interval, is called confidence interval. So what we're trying to do in this part of the lecture is to learn how to construct this interval, confidence interval, and then we'll learn how to use this to do hypothesis testing. So as I explained, to learn or to know how to do this interval, or how to construct this confidence interval, you need to understand, you need to learn about the variances and the standard error of OLS estimator, and you need to understand about the probability distribution of OLS estimator. So let's have the most basic example of regression model, which is a sample regression model, so as the one that we have now. So to calculate the variance of B2 here is the estimation of beta 2, B1 is the estimation of beta 1, and as I explained before in the lecture, just to remind you again, if you see beta 1 hat, this is B1, so it's the same thing, so the estimation of both means the estimation of beta 1, and the same thing for beta 2. So here, just to make it simple and easy for myself as well, just let's use the small letter B2 and B1 to refer to or to denote the estimation of beta 2 and beta 1. So the variance of B2 and the variance of B1 are given by these equations or by these formulas. So what I expect from you, I don't expect you to memorize the formulas, but I expect you to learn how to use those formulas to calculate the variance of B2 and B1. So let's look at the first one, the first formula, variance of B2, which let's call it sigma B2 squared, and this equal the sigma square divided by the sum of xi minus x bar squared, and we can denote this by just this italic x. So the same, we'll look at the same form, the other formula for B1, the variance of B1. So it's sigma B1 squared, and this can be obtained by multiplying sigma squared by the sum, by this part of the formula, which is the sum of xi squared divided by n. We understand n is the number of observation, sum of xi minus x bar squared. And again, you can just rewrite the same formula this way. So, but what is sigma? I believe that we understand now xi, x bar. We understand this now. But what is sigma squared here? You remember what we talked when we talked about the variance or the assumption of the classical linear regression model? We assume that the variance of the error term is constant, and we call it sigma squared. So sigma squared here is just the variance of the error term. So we have one problem in this equation. Only one thing we cannot obtain. If you remember, we do not observe the population, but because we do not observe the population, we look at sample. So because we do not observe the population, so then we don't know the error term. And if you don't know the error term, you have to make assumptions about the error term. And since you're making assumptions about something you don't know, the assumption is done based on what you expect about the behavior of the error term, which is you don't know. Then you need to test for those assumptions, and we come back to this later in the near future when we talk about some of those assumptions. But now let's just go back to the main assumption we made, which is the constant variance. So if I don't observe the error term, I cannot calculate the variance of the error term. But at the same time, we said that the residuals should be, which are obtained from the sample, they should represent or should be a good proxy of the error term. So instead of using the variance of the error term, which is something we don't know, we can replace this by the variance of the residuals, which we're gonna call sigma hat squared. So hat here means this is the variance of the residuals, and we can calculate this using this formula. So that formula here is the sum of the residual square divided by n minus k. To remind you, n here is the number of observation, k is the number of parameters estimated in the regression. So in our example, we have two parameters to estimate, beta 1 and beta 2, and that's why k here will be 2. So it will be n minus 2. So k is the number of parameters. So now once we have sigma hat squared, then we can use it here instead of sigma squared, and in this formula as well, instead of sigma squared. And that way we can calculate the variance of B2 and B1. But let me just explain more what we have here, what we've done here by adjusting the variance by n minus k. N minus k here we call it the degrees of freedom, and what we actually mean by the degrees of freedom. So before we calculate the residual, we need to estimate B1 and B2, and that way we lose 2 degrees of freedom from the data. So that's why k here is the number of parameters, and what is available now, it's n minus k. So it's n minus 2 in this example. So now having sigma hat squared, we can use the formula to calculate the variance of B1 and variance of B2. Then what about the standard error? So the standard error is nothing but the square root of the variance. So if you already have the variance of B2, so all what you need to do is just to take the square root of that variance. This will give you the standard error of B2. The same thing for B1. So you take the square root of that, you give you of the variance of B1. So that will give you the standard error of B1. Just remember what we have here is the standard error, not the standard deviation, because we use an estimation of the variance of the error, which is the residual, not the variance of the residual, not the actual error term, the variance of the actual error term. So because we do not observe the error term as we explained before. Okay, so now let's assume now we understand, okay, from sample to another, the values of beta 1 and beta 2 will change, but now we understand, or we know how to calculate the variance, which explain this variability. Then what kind of distribution this like the OLS estimator will have, that's something that we need to look at. So we need to look at the probability distribution of OLS estimators. So let's look at one more assumption now. We're gonna add to the four assumptions we had before. We explained the first part of this lecture and we cover in the previous lecture last week. So now we're gonna make one more assumption about how the error term is distributed, or about the probability distribution of the error term. So we assume that the error term is normally distributed around the mean. And the normal distribution, if you see this expression here, means UI, this is the error term. This tilde means follows. So it follows, N stands for normal distribution, and the normal distribution is usually defined by two values here. The first value here is the mean, and the second value is the variance. If you remember, we assume that the expected value of the error term, that's the second assumption, equals 0, and the third assumption was that the variance of the error term is homoscedastic or constant, which we denoted by sigma squared. So 0 here is the expected value of the error term as the mean, and sigma squared is the variance of the error term, which we assume that it to be constant, which we call sigma squared. So now, why is it important to understand the probability distribution? Because one of the things that we learn first, we need to first, before I go to that, we need to first understand why we assume that the error term will be normally distributed. Let me tell you why. The rationale of this assumption is provided by the central limit theorem, which says for a large number of independent and identically distributed random variables, there's something to follow a normal distribution as their number increases. So now we understand why the error term is assumed to be normally distributed. But again, how this is going to affect, or how this is going to enhance our understanding of the distribution of the OLS estimators, if a linear function of a normal distribution variable is itself normal distribution, so not normal distributed. So in the case of the linear OLS estimators, we can now, we know now that B1, so this is the estimator of beta 1, follows a normal distribution. What is the, how to define the normal distribution again? We look at the mean and the variance. So the mean, which is the expected value of B1, which we before understand that this is, if the estimator is unbiased, that the expected value of the estimator should equal the true value. So the true value from the population is beta 1. So that's why you'll see in this definition now that B1 follows normal distribution with mean beta 1, so that's the expected value, and with variance of sigma B1 squared. And we already know how to calculate the variance. So you remember the formula we had to calculate the variance for B1. The same thing for B2. So B2 also follows a normal distribution with expected value beta 2, which is the true value from the population, and the variance, which is sigma B2 squared. And again, we know the formula how to calculate now the sigma B2 squared. So let me now move to a different, to the next point, which is how to standardize, how to make a normal. So these two follows normal distribution. So how to make a normal distribution, how to convert it to a standard normal distribution. So one thing you need to do is to subtract the mean and divide by the square root of the variance. And in that case, so the standard normal distribution will have a very like specific characteristic here, which is a nice property here, which is the mean will equal 0 and the variance will be 1. So what we did here, we just subtract. So you here subtract the mean, which is beta 2. If I'm doing that for B2, so B2 minus beta 2 divided by the square root of the variance of B2. Then this should follow normal distribution with mean 0 and variance equal to 1. So just to explain this for, if what we did here is just we turned this one, the normal distribution, to a standard normal distribution. Just notice the mean here. So if you subtract the mean, so that means 1010 minus 1010, this will convert this to 0. So the mean will be 0 and the variance will be 1. So why we need to do that? One reason to do that, because for that kind of distribution, there are some properties that we know and we can make use of. One of which here is that what you can see now on this slide is that 68% of the values are within one standard deviation of the mean, so around the mean, and for 95% of the values will be around 2 standard deviation of the mean, and 99.7% of the values are within 3 standard deviation of the mean. Just remember what we're trying to do here. We're trying to construct that interval, that we're trying to be somehow confident or with some kind of probability that the true parameter will lie between these two values here. And that's what we're trying to do here by looking at the probability distribution of the always estimator. One thing to recall at this point is that when we actually we calculate the value, the variance of B2, we need to estimate it based on we didn't use the sigma square, we used the sigma hat squared, and that's why we have here the standard error rather than the deviation. So we have the standard error of B2, and that make this the distribution we have here a bit different from the standard normal distribution. It will follow a different distribution called t distribution with n minus k degrees of freedom, and still some of the, so you can see here is just exactly like very similar form. We have B2 minus beta 2 divided by not the variance, we divided by the standard error of B2. And this means follows t distribution n minus k degrees of freedom, and we understand before that k is the number of parameters we estimated. So in our example, if we have 2 parameters, k would be 2. Then we can use all this information to construct that that interval or that confidence interval for beta 2. So if you see that formula here, what we have is the probability that t is more or less greater than or less than minus t alpha divided over 2, and less than or equal t alpha divided by 2. This should equal 1 minus alpha. Here is the significance level. So let's say to construct the 95% confidence interval, that means alpha should be 5%. The 1 minus 5 is going to give you 95%. That is the probability that or this value should be within or lie with interval. And just before, and just to explain this values we can obtain from the table, from the table. So you don't worry about how to get these values. I'm going to show you how to do this. But first, let me just T is here we have B2 minus B2, the standard error of B. So we can include this in this formula range. This will give you formula here that the probability, this is beta2 as the true value, and that's the value that comes from the population. And now we have two values around these values. So this is the lower bound here, and this is the upper bound here. Just notice that these two are exactly the same, except for this is minus and this is positive. And this, of course, this probability will be minus 1 minus alpha. I can explain alpha is 5%. So that means I'm looking at the confidence interval for 95% confidence interval for beta 2. So we can write the same formula in a more compact way. So we can say B2, oh, this should be between, for beta 2, so B2 should be plus or minus this value that we obtained from the table, and I'm going to show you how to get it from the table now, times the standard error of B2. So this is how the distribution looks like, and if you want to look at this here, this point here, this is the lower bound, this is the upper bound. So if I'm looking at 5% significance level, that means this area between here, this means this is the 95% chance that, or probability, or we are confident, 95% confident that the true value of the beta will lie between or within these two, within this interval or between these two values. So let me now show you an example how to get this value. Let's assume we have alpha 5%, degrees of freedom 24. Then we need to look at two-tail test, and we'll explain next lecture why we're looking at two-tail test, and then when we do the t-test, we're gonna explain why. And let's now look at 5%, and the degrees of freedom in this column here is 24. So we need that value. So that means t alpha here, which is 5%, and the critical value, which is t in that formula, is 2.064. So that's an example how to obtain this, t critical from the t distribution table. So now let's say we can do the same for beta 1. So we can construct a confidence interval for beta 1, and again, why we're doing that? Because we're trying to see how reliable our estimate is, and how to say that we, for 90% or 95% confident that the true parameter, if not equal that value that we get from the OLS estimation, it will be somehow between those two values or within this interval, and we need to know how much we should be confident about that. So let me do this, finish this part of the lecture with an example. So let's assume that this is the model we have. So this is yi equal 83.42. So this is the estimation for the beta 1 plus 10.21, which is the estimation of beta 2 xi, and we know, let's say we have the standard error is given for B2, and the number of observation is 40. So how to construct the confidence interval for beta 2? So to do that, so again, I just wrote everything we know here, and what we have here. So this is the standard error of B2, and this is the value of B2, which is 10.21, and there's a standard error of B2, which is 2.093. What I've done here is just give you the value for the t critical, which comes from the table, and how to get this again, if you remember the table. So we need two things. You need alpha, which is here 5%, and you need the degrees of freedom. So the degrees of freedom is n minus k, and since that n is 40, that's the number of observation, and we have two parameters we estimated here, so k equal 2, then the degrees of freedom will be n minus k here, so 40 minus 2, this will be 38, so the degrees of freedom here is 38. So if you go 38 and 5%, this will give you 2.024. And if you get this value, then you can very straightforward. You can just apply this formula. So the probability. Remember why this is 0.95, because this is 1 minus alpha. Alpha here is 5%. So that's what we're trying to have here is the 95% confidence interval of beta 2, and the easiest way to do that, so you have B2, which is the estimation of beta 2. We have from all this estimation, which we have from the equation, plus or minus, and this is the critical value we get from the table times the standard error of B2, which is given. By doing that now, just see, so that's the lower bound of the confidence interval, which is 5.97, and this is the upper bound, which is 14.45. So let's see the value that we have from all this estimation is 10 for beta 2 is 10.21, and the confidence interval is 5.9. So 5.9, this is the lower bound, and 14.45, and B2 is 10.2. So what we're trying to do here, we're saying 95%. We are confident that the true value, which is beta 2, if it is not 10.2, it will be between these two values, which is 5.97, that's lower bound, and 14.45. So 95% we're sure, we're confident that the beta, the true value from the calculation will, of the parameter that comes from the calculation, will lie within this interval or these two points. And in that way, we can judge, we can see how reliable our estimates are of beta 1 and beta 2. So of course I've done here the confidence interval only for beta 2, but in a similar way you can do the you can construct the confidence interval for beta 1. So now we understand, or in this part of this lecture, in this video, I just show you how what's the difference between the interval estimation and the point estimation, and why we do the interval estimation, and I show you how to construct the confidence interval for OLS estimators. The next lecture I will take you through the hypothesis testing, and I'll show you how we do hypothesis testing using the confidence interval, and how to do the t-test or the test of significance. And we'll finish the lecture next time, or the next lecture, with the goodness of fit, how to judge the regression line we have, whether how will it present or represent or fit the data we have. Thank you for watching this video, and I will see you next lecture this week on Thursday. Thank you.